Hi, my name is Simon Garhofer. I'm from the University of Tübingen, and this talk will be about scaling combinatorial optimization problems on NISQ computers. As you may know by now, quantum computers that currently exist have two main issues. One of them is their very limited size, and the second one is the noise that comes up during computation. And the first issue, the problem of limited size, is the one I'd like to address with this, using classical algorithms that decompose larger problem instances into smaller ones, which I will then put on a quantum computer to solve. And the example problem that I'm going to illustrate this with is the traveling salesperson problem. I chose this problem for three main reasons. One is it finds widespread application in practical use. Two, it has there's already much theory done on it previously, so we know a lot about this problem. And three, of course, it is difficult to solve on a classical computer, so it makes sense to try and throw a quantum computer and at it and see what happens. Now, the problem statement itself, if you're not familiar, is you have a set of points on a map, and your task is to find a path that visits each of these points exactly once, and the length of this path must be minimal. And so this is difficult, and the main idea to tackle this is here, because this problem size already won't fit on a quantum computer that we have today. There's too many points. So as an idea, what is already doable is 4 points. These 4 you could put on a quantum computer and try to solve, which is not many. So the main idea is this. I take a combinatorial problem instance like I had before, and I first decompose it into many smaller problems on a classical computer. And these small problems will then be of such a size that I can fit them on a quantum computer currently existing. And now all of these problems hopefully yield some solutions, and these solutions then need to be recombined on a classical computer as well. And of course, the point of this is that the strengths of both systems can be put to use. So the decomposition and the combination of solutions is quick on a classical computer. And also a classical computer can hold the whole problem in memory, while a quantum computer can't. But the combinatorial core of the problem, like the thing that is difficult about it, we can put on the quantum computer. And here is an overview of what this looks like, or like an idea of how it works. And if you're familiar with computer science, you may know the algorithm called A star. And if you don't worry, I will go through each of these steps individually, and I hope it will make sense to you either way. But A star is a pathfinding algorithm, and the high-level idea of this is that you generate several small subproblems of the big problem. So this is the big problem that comes in, that gets split into subproblems, and these subproblems you can build a graph with. And through this graph, if you find a minimum path. This minimum path corresponds to a minimum solution to the original problem. One benefit of this is that you're not restricted to a specific algorithm for your quantum computer. So you can use QAOA, which is what I did. If someone comes up with a different algorithm in the future, or you want to do a crossover search, for example, you can do that as well. So that is not of concern. So for the first step, generating initial nodes. So in this step, we create a base, so to speak, to work from on our minimum path search. And the way this is done is I draw a rough sketch of the path that I'm trying to find. So a rough sketch of the minimum path, and I choose several candidates, which are these initial nodes right here. And like these colorful dots, they just mean that I choose a very small subset of this into many candidates that I'm going to use. And basically these candidates draw a rough sketch of my intended path in such a way that between each of these points, so between yellow and green, and between green and brown and yellow, in this instance, we generate actual subproblems that can then be solved on a quantum computer. After generating all of these initial nodes, we evaluate the utility of those nodes. And by utility, I mean is how long do we expect this path that we just chose as a candidate to be. And this expectation is computed not only dependent on what our candidate nodes be, but also all of the nodes that are not in our candidate set. And the combination of those yields some estimation. In our case, for the TSP problem, we did that using a very small neural network that takes as input some high-level features of a TSP, for example, the number of nodes you have or the average distance between two nodes. And in the third step, we take the node that we estimated the best score for. And this is the first point where actually quantum computing comes into play, because then we can generate a subproblem which is then solved. So here, with solving, I mean this is the first time a quantum computer is used. And this also yields then some subsequent nodes, because then you see, okay, we have put a subproblem into a specific order, which is indicated by this rectangle, so they no longer float freely in this circle, but they are in a specific order. And onto that specific order, we also want to add a few more of our points from our original problem. So this node in total becomes bigger. And then step 2 and 3 basically iterate. So then for all of these points, again, we estimate their utility. And of course, if this node is bigger, this node must be smaller, because fewer points of our original problem are left. And our algorithm basically terminates if this set is empty and this set contains all nodes. And this is an illustration of what you get when you do this. So on the left side, there is a randomly generated TSP instance with 17 points. And the optimal solution is here drawn in orange. And on the right side, a different solution, an approximation, is depicted where the different subproblems that were generated along the way are differently color-coded. And as you can see, these different subproblems I've also solved with QAOA on a simulator. So, and since QAOA is an approximation algorithm, you don't necessarily find the optimal solution like from here to here, but it does some kind of zigzag that is not really necessary or advantageous. But what you can see is that the idea, so to speak, of the optimal solution, which is to go around this graph, is still retained. So even though the way we solve this problem on a quantum computer is not optimal, this comes really close to being optimal. I think this one has a length of 70, and this one should be 76 or 78, so it's not too far off. Yeah. That's also already it. So I thank for your attention, and I'm open to questions if there are any.
Hello. Thank you. That was a very nice talk. I have a question. Could you please go back to the slides with the problem, with the traveling system? Yeah, exactly. This one, yeah. I have a question. So, is it really a problem of the QIOA algorithm that you don't find a local minimum for the segment, or is it more like how you divided the problem?
No, because if I divide this problem like from this point to this point, the optimal solution should always be here, 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 here. Like how I divide the problem does not do anything with how the subproblem is solved. So this is not solved optimally, obviously, which is down to QAOA, yes.
Mm-hmm. Okay. And when you divide this problem, do you have some consideration, some pre-processing, or do you just say this? Each 4 points which are close to each other should be optimized individually.
Again?
So how do you divide the problem into small instances? Do you do some estimations, some coupled clustering of the things?
Good question. So in this generic setup, there are no considerations concerning what points go into a group and what don't. But as you might be able to imagine, if you do that, you get a very large number of nodes that you then have to search through, which in the worst case actually ends up being way slower than just solving the problem outright. So what you really need to do is exactly what you said, to do some pre-processing, to say, okay, I only want certain groups of points in a node which that makes sense to go together. And in this case, I actually did a nearest neighbor search for each point. So each point only has its nearest neighbor in one such node, because the intuition is, okay, an optimal tour will not go through this point and then here and then back up here and then here. The tour will visit somewhat points that are close to each other, but also not necessarily the closest point.
Okay, thank you.